Billions of years ago, the Martian surface hosted a highly active hydrological cycle. The geomorphology of Jezero Crater and the sprawling river network of Nuredova Vallis point to high-volume liquid water flows during the Noachian and Hesperian periods. NASA's Perseverance rover is currently mapping this terrain, analyzing the sediment left behind by those ancient rivers. Its investigation centers on rocks like Chayava Falls, an arrowhead-shaped sample carrying potential chemical fossils. High-resolution scans of the rock reveal distinct millimeter-scale patterns known as reaction fronts. These leopard spots mark the precise boundaries where physical and chemical reactions altered the rock's composition. The spots carry the signature of two iron-rich minerals, vivianite and greigite. To form these specific compounds within a sedimentary matrix, a reaction requires organic carbon, sulfur, and phosphorus. These are the exact chemical inputs required to fuel simple microbial metabolisms. On Earth, identical iron sulfide and iron phosphate reaction fronts are consistently found in oxygen-depleted bogs and sediments, acting as definitive markers of bacterial activity. This sedimentary record proves that early Mars provided the chemical equilibrium necessary for life. Today, however, the planet's surface is a sterilized sub-zero desert, heavily bombarded by solar radiation. The surface biosignatures confirm a wet, reactive past. Yet the total disappearance of the surface oceans responsible for these formations presents a profound mass balance problem. The water had to go somewhere. Geomorphologists calculate that carving the massive global valley networks observed on Mars required a highly specific planetary water volume. We can quantify this required volume and compare it against where the water is today. Mars required a global equivalent layer, or gel, of at least 640 meters. Solar winds stripped 200 meters away and 550 meters locked into the crust. Subtracting losses leaves a massive gap of 710 to 920 meters of missing water. The modern surface inventory cannot bridge this deficit. Even if you melt every trace of polar ice, subsurface permafrost, and seasonal frost, it yields only 20 to 40 meters of water. The physical mass of a planetary ocean does not vanish without a trace. If hundreds of meters of global water still exist on Mars, they must be sequestered deep within the architecture of the lithosphere. Tracking down this missing mass requires looking past the dry, fossilized surface and physically probing the planet's deep crustal interior. Ground-penetrating radar from orbital satellites provides a limited view. High-frequency waves attenuate rapidly in rock, restricting mapping to the top few kilometers. Deep crustal investigation relies on measuring the propagation velocity of seismic waves. For 4 years, NASA's InSight lander operated as a stationary seismological observatory to map these internal structures. Early models relied on low-frequency waves from deep tectonic Marsquakes. Because long wavelengths lack fine spatial resolution, these models could only divide the crust into thick, uniform blocks, failing to resolve the critical boundary at the base of the upper crust. To achieve higher vertical resolution, geophysicists shifted their analysis to high-frequency seismic data, specifically isolating wave signatures oscillating between 0.25 and 4 Hz. Generating this kind of sharp, high-frequency energy requires specific trigger events. The data came from a highly energetic, shallow tectonic Marsquake, combined with the seismic shockwaves of 2 meteorite impacts. These events propagated through the upper crust beneath Elysium Planitia, an area bordering dense volcanic provinces. Because high-frequency waves have shorter wavelengths, they interact with smaller, thinner structures. They scatter and reflect off minor density shifts and material boundaries that low-frequency waves simply pass through. Researchers process these reflections using receiver function inversion. By separating the primary seismic wave from the waves that convert their energy as they hit geological boundaries, they calculate the exact depth and density of hidden rock layers. By utilizing meteorite impacts as planetary-scale ultrasonic probes, the team secured the vertical resolution necessary to image the very bottom of the Martian upper crust. The inversion revealed a massive structural anomaly. Starting at a depth of 5.4 kilometers and extending down to 8 kilometers, the shear wave velocity drops dramatically. In rock physics, seismic velocity is governed by the elasticity and density of the medium. A pronounced low-velocity zone at this depth indicates a highly fractured, porous rock matrix that is fully saturated with a fluid. The critical question is the phase state of that fluid. To determine whether this deep reservoir consists of frozen ice or liquid water, we have to look at the geothermal gradient. This chart plots the thermal profile of the Martian crust against depth. The surface of Mars is fiercely cold, pulling the upper crust well below the freezing point of water. But as depth increases, planetary heat raises the temperature. At approximately 5 kilometers deep, the red temperature line crosses the black freezing threshold. Below this threshold, the ambient pressure and geothermal heat ensure that water cannot freeze. Any fluid contained in this low-velocity zone must be liquid. The seismic data defines an aquifer layer approximately 2.6 kilometers thick. Based on wave scattering models, the rock at this depth maintains a high porosity, consisting of 20 to 30% empty space. Assuming this porosity is globally representative, a reasonable assumption given the heavy asteroid bombardment that fractured the early Martian crust, we can multiply the thickness by the saturation volume. A 2.6-kilometer layer operating at 20 to 30% liquid saturation equates to a global equivalent layer of 520 to 780 meters of water. This finding aligns with the missing 710 to 920 meter deficit. The seismic observations place the found mass directly within the expected range of the planet's missing water inventory. The evidence suggests that the bulk of missing Martian ocean is sequestered inside a global, deep crustal reservoir of liquid water. Confirming a massive liquid aquifer redirects the search for extant Martian life. Future missions must identify regions where this deep water intersects with available energy sources. Astrobiologists have identified Acidia pronetia as a primary target. Geological modeling suggests the boundary where subsurface ice transitions to liquid water is exceptionally shallow here, sitting beneath a crust highly enriched in radiogenic isotopes. Because this environment is entirely isolated from sunlight, photosynthetic energy is impossible. Instead, the system relies on heat-producing elements buried in the rock, primarily isotopes of thorium and potassium. As these elements decay, they emit radiation into the surrounding saturated pores. This radiation physically shatters the water molecules, a process called water radiolysis, continuously releasing molecular hydrogen into the fluid. Molecular hydrogen is a highly potent electron donor. On Earth, it forms the basal energy source for chemolitho-autotrophic life, organisms that eat rock and gas to survive. In this model, the Martian aquifers operate as vast, planetary-scale chemical reactors, constantly generating the abiotic fuel required to power a biosphere in absolute darkness. We have living analogs for this environment on Earth. Deep hypersaline anoxic basins, or DHABs, are oxygen-free, hypersalty water bodies buried deep beneath the Mediterranean seafloor. In these crushing, nutrient-starved conditions, specialized organisms called methanogens thrive. They extract energy by reacting molecular hydrogen with carbon dioxide, producing methane as a byproduct. This informs the biological retreat hypothesis. As the Martian atmosphere thinned and the surface froze billions of years ago, any existing microbial life would have followed the water, migrating down through the heavy fracture networks caused by impact craters. Until now, the deep aquifer was purely theoretical. The high-frequency seismic inversion from InSight elevates this from a hypothesis to a physical location, confirming the exact depth and volume of a present-day habitable niche. The dry channels of Jezero Crater and the mineral reaction fronts on Chayava Falls provide snapshots of the planet's history. They document where life was once viable. The Martian water cycle continues within this vast, saturated lithospheric sanctuary, sheltered from the radiation and cold of the surface.